Welcome back, everybody. So we're in the final section here. We're going to look at these last three examples where we've got infinite discontinuities. So let's go ahead and jump right into them. So number one, we've got this natural log of x dx. So we're going to have to use integration by parts for that example. So we'll do that one a little bit later. Let's start with the other examples first. So we've got integral from 0 to 2 of 1 over rad 4 minus x squared dx. And so we'll note that our value that's going to be undefined is not 0, but rather it's going to be 2. So at 2, we're going to run into this 1 divided by 0 expression. So we're going to rewrite this then as the limit as t approaches 2 from the left. So note, 2 is our right endpoint, so we're going to be approaching it from left inside the interval. And then we'll have the integral from 0 to t dx over rad 4 minus x squared. And we can see that this is going to be an arcsine function. So we'll have the limit as t approaches 2 from the left of arcsine of t over 2. Arcsine of x over 2. And then we'll have to evaluate it at t and at 0. So then we'll get arcsine of t over 2 minus arcsine of 0 is just 0. And then substituting in t is 2, we'll get arcsine of 1, which is going to be pi over 2. So this integral is going to equal pi over 2. And again, definitely worth graphing the function to see what it looks like. But this is going to converge. All right, so let's look at example 3. So for this one, by our p series, we can kind of think, or not p series, sorry. By our expression, we can see that we're going to get a natural log. So that's, that's going to make it so that you might think that it doesn't converge. So let's just note that our discontinuity is at the left endpoint. So we're going to be approaching 1 from the right. So we get integral t to 2, 1 over x minus 1 dx. So this is going to work out to a nice natural log of x minus 1 integral from t to 2. So if we look at our expression here, we're going to end up with the limit as t approaches 1 from the right, and we're going to have the natural log of 2 minus 1 is just the natural log of 1, which is 0, minus the natural log of t minus 1. And we can see that as we approach 1 from the right, t minus 1 is going to approach 0 from the right as well. And we know that the natural log is going to approach negative infinity. And so because this is the opposite of the natural log, we'll get that this equals positive infinity. And so it diverges. Okay. And then our last example we'll look at, this first one, is the natural log of x. So note, we can do a bit of work ahead of time with the antiderivative with by parts. So we'll let u equal dx and dv, we'll let u equal the natural log of x and dv equal dx. So then du is going to be 1 over x dx, and v is going to equal x. So then we would get that this is going to equal x, natural log of x, u times v, minus integral v du is just going to be 1 du, so we're going to get x natural log of x minus x dx. Oh, minus x, sorry, plus c. And that should be dx. Yeah. So we know it's going to be x natural log of x minus x as our antiderivative. So again, doing that side work ahead of time is probably a good idea for this example to save space, but you can kind of do it later on if you wanted to. So then we'll take that work and we'll carry it over to our actual work for evaluating this integral. So we're going to have the limit as t approaches, and then we can see that the natural log is going to be approaching negative infinity as we approach 0 from the right. So we'll have the integral from t to e, natural log of x dx. So then we'll have the limit as t approaches 0 from the right of x natural log of x minus x from t to e. Okay. So let's go ahead and work this out. So we're going to have the limit as t approaches 0 from the right. We'll have e, ln of e is 1. So it'll just be 1 minus e. So we've got this e minus e expression. Minus, and then at t, we're going to have t ln t minus t. So this is just going to be 0. So we'll have the limit as t approaches infinity from the right, or sorry, 0 from the right, of negative t ln of t plus t. Now the 0 is just going to become 0. But now the question is, what about this t ln of t? So, because t is approaching 0, but ln of t is going to be approaching negative infinity. So we're going to have to apply L'Hopital's rule here for that term. So we can split the limit as each one of those terms, and then we know that this value is just going to equal 0. So it's going to disappear. So let's go ahead and get to the limit as t approaches 0 from the right of, we can write this as ln of t. The negative sign doesn't matter, so we can just leave it in the top of 1 over t. And then by L'Hopital, we'll get the limit as t approaches 0 from the right of, it's going to be negative 1 over x over negative 1 over t. So negative 1 over t over negative 1 over t squared, which is going to equal the limit as t approaches 0 from the right of just t, which equals 0. So this does converge. It does take a little bit extra work to get there. So the integral from 0 to e of ln of x dx is going to equal 0. So let's go ahead and take a look at that. So we've got the natural log of x. Oops. Let's do f of x. Do natural log of x. And we can restrict it between do x less than e. Oops. Which is very interesting. So we get this graph, and so what that means is if we integrate from 0 to e, those areas are the same. Right, so this little area on the right is the same as that infinite area on the left. Very cool. All right, so that's going to end our notes for improper integrals. So again, if you have questions, shoot me an email or come by the office hours. And otherwise, until